Hi everyone, sorry for the title so long. So my name is Huda Shaji. My supervisor is Dr. Leibler, and I'm going, as my friend said, I'm going to talk about optimizing probabilistic feedback controller via Kullback Leibler divergence minimization. So first of all, we're going to the outline. Let's go back to outline. So we'll talk first. We'll get motivation example, for motivation example. Also, we will introduce very important control tool that and strategy that will depend highly on this design controller, which is a model predictive control. And also we'll go through how we design for probabilistic control, and then we will go to derive our optimization problem and solve it through model predictive control. Then we'll share some results and we go and end up with a conclusion. So our motivation example that we will depend on modeling problem, and it will be car cross controller. So as you can see here, for our ordinary differential equation, we will see that, as we can see here, this is the car, and we want to consider the forces that apply to the car. So here we have the engine forces here, the engine force, and the air drag, and it will be in negative direction, and will be proportional to the velocity of the car. Also we have friction, and at the end we will consider the wind, and the wind will be as a disturbance to our system. And from Newton's second law, we follow Newton's second law to write our ordinary differential equation, and which is say basically sum of the forces equal mass time acceleration, and we represent acceleration through the change of velocity over time. So here we have change of velocity over time, and here we have sum of forces that we consider in this car cross controller. And then what we want, our aim in car cross controller, is that we have certain velocity and we have actual velocity. So we have F reference and F actual. And what we would want to do is to make the difference between them to zero. So our state will be tracking error. Our state would like to make this error going to zero. And how we do that? The input for our system, it will be the forces, engine force. So, and we will design it to in this form to be a feedback gain K time X, which is the tracking error, plus some R, which is will be highly depend on it on model predictive control, because this will help us to forces constraint to our system. And since we are considering disturbance, the wind in our system, we will also design randomized disturbance here. We'll follow normal distribution with zero mean and covariance pi. And since our ordinary differential equation and continuous time in our system in FBC, we usually depend on discrete time. So we would like to use a quick formula to just approximate the continuous time, the discrete time, and try to write it in this form. Once we write it in this form, so we have difference equation, non-differential difference equation. So from here, we can design our controller. How we will design our controller? Before we design our controller, I have to introduce the model predictive control. So I'll try to draw this picture here to help us to just a quick introduction. What is model predictive control? So suppose we have initial condition for the system of xk. We take this initial condition, we do optimization here, we apply optimization strategy, and we will have what over time horizon. So this is our first horizon for the time. What we'll have sequence of input. In model predictive control, we usually take the first one, apply it to the system there. Then what we take the next step. We take the next step forward. So we will take this one forward, and then what we will do, this one will be our new initial condition. We apply it here again, we do optimization strategy. After we shift the time horizon forward in time, then we get a new sequence. We repeat the procedure same again, until we reach our goal. And here this line represents for us constraint. So what goes in model predictive control that we can apply constraint. Here, now we're going to designing our controller through probabilistic control. How will we do that? First, we will consider difference equation for our system. So this is our system, and here we have the disturbance WK, which follow normal distribution with zero mean and covariance sigma. This represents for us the wind that we saw in the car cruise system that we just introduced. And then what we will do, we will design this input. And this input, as I said before, it will be K, which is the feedback gain, that we will assume that for our system here, for this presentation, that we already have it, and for it's of unconstrained optimization problem for probabilistic control, we can do it offline, we will get it. And then we will have RK, which is the correction that will allow for us to put the constraint, and here as I said, the design disturbance here. Then we need to consider the system transition density in our work. And in our work, we will assume that it's Markov. So basically, it's the future depend on the current, the future depend on the present. And it will follow normal distribution. And the mean is AXK plus BUK, and the covariance will be sigma. And also we'll assume the sigma will be positively finite. And it's very important for our design controller here to be positively finite. And also we will consider what, as we said in car cruise controller, we have a reference like ideal speed. So we will consider ideal system, usually in BC for probabilistic control, we consider what? We consider ideal system. And ideal system, same thing, Markovian, future dependent present with normal distribution, zero mean, and sigma 2. This is our ideal system that we want to reach. Also, we have ideal controller, and the same thing, but ideal controller would depend on XK at 10K. So UK depend on XK, and it will follow normal distribution with zero mean and covariance gamma. And what we want to do, again, I'm repeating, we want to design the controller. This is the actual controller, but rather than transition density, it will be normal distribution with mu as a mean and covariance, pi as a covariance. And here, this is the mean, KXK plus RK, and the covariance by K. In order to do that and formulate our problem, formulate our cost function, we need to have the joint closed loop description here. So here, let's agree that we will call this one the actual, and this one will be the ideal. So it will be the product between actual system, actual controller, and here will be product between ideal system, ideal controller. And from here, as we said in the title, we will have Kullback divergence. So we will use it here. As we saw, we agreed that this is the actual, and this is also the actual. We have len here, we have ideal. From our assumption, we assume that the system is normal, the controller is normal, ideal system is normal, ideal controller normal. We will substitute here. We will do a lot of simplification to just transform it to this long and function, and that we will depend on it. Nothing to be scared about it. So it will depend on it to an optimization problem. If you focus a little bit here, we can see here that here is the quadratic term weighting by the ideal system covariance. And this quadratic term, this is the mean of the system, and this is the ideal covariance. And here, this quadratic term, mean of the input, and this is the ideal covariance for the controller covariance. And here, those two terms here related to the covariances that will help us to measure the covariances, help us to measure the mean. So we will simplify again. So this one, the long one, we will transform it to another one use it to transform it to another one. So we will work on this part, this two quadratic term, because we have R there. So we want to simplify it in terms of R. And this one, we will assume this one fixed, we will assume this one fixed, just to focus on how we get optimal covariance for our controller by K. Let's work through that. And not only that, also we want to do prediction. So here will model predictive control come. So we will work on it to predict on this mean state, and we predict a mean input. First of all, let's go to the first part. We will demand that our mean input, or this is I for the time horizon that I talked about it. So we will say Zi plus 1 given K will equal phi Zi given K plus Bri given K. Then we go for the next step, would be Zi plus 2 given K equal phi Zi plus 1 given K plus Bri plus 1 given K, and continue like this until we reach end step. And we can see here, from here, we have term related to Zi plus 1 given K. So what we will do with it, we will substitute this term here, and we simplify it, and we get nice form for it. Do the same thing for here. After we simplify this one, substitute here, and continue like this until we reach our horizon. So we will get this matrices. So we will call the first one as O1, and this one we'll call it M1. And we write it in compact form like this. So we get the prediction for the mean state, and we wrote it as a compact form. Then, because I'm focusing on R, and in my cost function, as we saw, we have quadratic term. So we will multiply with, we'll make it quadratic, and we weight the covariance, the ideal covariance in the middle. We use canonical product just to fix the dimension problem. And we see here, we can write it in this term. We have R here, we have R here. So we have quadratic in R. We have R here, and we have linear in R. And there's no R here, so to be constant. So we can write it in this term. The first part of our cost function related to the state. We can write it in this term. We do the same thing for the second part, with the second quadratic term for the mean input. We write it in the We do the same prediction as we said before, and we write it in this matrix form. Then we check where is the quadratic term in term of R, where is the linear term, and the constant. We name the quadratic term H2, we name the linear term F2, then we can write it in this form. After doing that, we will add the first matrices H1 plus H2 will be our H, F1 plus F2 will be our F. Then we transfer the big function for Kullback Leibler to this form. So we can see from here, we have this part that we worked on it. This will be constant. This will be related to the covariances. Our aim is to do this optimization problem now. After doing model predictive control, we will do this optimization problem. We will get optimal R, optimal covariance. When we do that, we know that our actual controller is normal. It's so high. We can write it if we know the mean, and covariance we can write our controller. So we got the way why we assume that it positive define the covariances, and we got quadratic function, so we can get the gradient to 0, and we will have unique solution for our optimization problem, and it will be this one minus H1F. Yeah, and this is our optimal R in terms of the matrices that we wrote it. So our optimal mean for the controller will be Kxik minus R star. It will be plus R star, but since we have here minus, so it will be minus this form. Next, we didn't finish until now. We want also to work on the trace term and blend term that related to the covariance. So we collected them here. It will be complex, so we can solve it also and take the gradients and make it equal to 0, and we get the optimal covariance here, formula for optimal covariance. Then we can write our optimal controller in a closed form. So we have optimal covariance here, and we have optimal mean here, using, of course, the probability density function for normal distribution. After we're doing that, this is unconstrained optimization problem. But here, why we did all of this work to write it in terms of R, because we want to force the constraint. So we can force the constraint. We can write it in this form. And this is typical model predictive control problem now. So we have minimizing the cost function, subject to we constrain the expected value, which is the mean for the input, to between two new max. Also we constrain the expected mean for the state to be between Z min and Z max, and we constrain the covariances. And these are hard constraints. So in this design, we are forcing hard constraint. Just because we did all this work, we can write the constraint here for the mean and input and mean state in this form. So here, little bit simplification, we can write everything in terms of R. And then we can apply the constraint optimization problem. And since it's quadratic, we can follow active set method. Active set method in numerically, we'll solve typically in MATLAB, we can solve it. Here, block diagram, just to summarize all the work that we did here. Suppose we start from initial condition, we do optimization loop for model predictive control. We got optimal R optimal covariance. We will substitute it here to get the input, and it will be follow normal distribution. And here we will get the next actual state after we substituted the input. And we'll get normal distribution. Then this is next state. We'll reinitialize. This will be our new initial condition, and repeat everything again and again until we reach our goal. This is the result that we got it from our numerical solution. So first of all, here we have mean input, and here mean state. The expected value for the input, expected value for state. This is hard constraint that we forces for the mean and for input and state, mean input and mean state. And we can see here how our goal that we want to reach mean zero. So we are reaching mean zero, and we following the constraint. We're not following the constraint. But we will also see this figure, because our system is stochastic. This is represent for us the actual state. So we can see here some limitation of our work. What? Because we forced hard constraint, and the stochastic hard to control it like this, or we force hard constraints. So and if you have confidence region here, you can see that we have some violation for the constraint. And one idea that will be good for our future work is not only consider hard constraint, is to consider chance constraint, which is probabilistic constraint, but it will be like if we force the probabilistic constraint, it will be like trade-off between performance and between following constraint. So if you would like to sacrifice a little bit from performance, then we apply probabilistic constraint. This is the conclusion. What we did now, we've reformulated feedback control as distribution matching using Leibler divergence. We derived a complex quadratic problem and a model predictive control under linear Gaussian assumption. So it's very important that our assumption here linear Gaussian. We also obtained closed form control law. And future work, as I said, we can extend to formulate to chance constraint also our program, and maybe nonlinear. We consider nonlinear system with multiplicative noise. And also we could study, which is very important to study, the stability and feasibility for our system. Yeah, thank you. Yeah.
Thank you very much, Huda. Do we have any questions from the audience?
Yeah. Sorry, this is probably quite a naive question, but in the state vector for the car, what is that just the position, or is it the position and the velocity, or is it something else?
So we go for motivation exam, right?
I guess, yeah.
Yeah.
Or okay, so I guess you did it on a sort of abstract system when you finally finally did it?
Yeah.
Okay.
Yeah, and just we wrote it and just to read it, we introduced it just to write it on this form.
Mhm.
Then we will work on it. Yeah.
Okay, because I was wondering if you had a force that was directly modifying the car.
Yeah, the engine forces that.
Yeah, and so I was wondering if it was affecting the velocity of the car or the position of the car or.
We are focusing on velocity of the car.
Yeah. Okay. Oh yeah, of course you were.
Any other questions? Okay, I can ask one more. You mentioned an ideal scenario of controller. What was the assumptions of that ideal controller, and like what goes wrong when you don't have those assumptions? Just briefly.
Yeah, we are assuming that we have ideal controller, we have ideal system, and the assumption is that it's following normal distribution. This is a very important assumption, and the mean for it is to be 0. The mean for the ideal controller and ideal system to reach state 0. So when we
and positive definiteness of covariance.
Yeah,
That's all. Okay.
Yeah.
Okay.
Yeah.
Thank you.
You're welcome.
What breaks down when you don't have the positive definiteness?
So the quadratic problem, we wrote it there. Maybe we couldn't find the unique solution for it. And also in probability density function for normal distribution, we need covariance to be invertible. So in order to use probability density function in Kullback-Leibler, so as we said here, we had the Kullback-Leibler here. So we substitute the probability density function for each one of them. So that's why we needed to be positive defined.
Thank you.
Welcome.
Yeah.
Yeah, sorry, it was just to follow up on that normality assumption. Is that normality around some constant level? Or because like if wind's gusting, I guess it normally comes from, say, approximately the same direction each time.
So can you explain your question again?
I guess with the gusting of the wind, I'm surprised that it's normal, I guess is the observation. I would have expected to always be from one direction.
I know, I understand the question. So this is very simplified one. So we assume with the disturbance, we consider the wind, it's normal covariance for it. But in real world, maybe it will not be like in the same direction. So will be multiplicative noise. So we will consider, that's what we will consider in future work. Hopefully, yeah.
Do you have any idea if this would work if it was like a heavy tail distribution or something? Would you still expect it to work reasonably well, or would it go completely?
So it will be a little bit modified. So what I'm doing now with my supervisor to write the general form for it for different distributions.
Okay.
Not normal. So after we do write the general law for it, we'll check how we will apply the model-based control. Do we have the quadratic problem again, or maybe not quadratic? So we'll check that.
Yeah.
So, but now we have quadratic because we are depending on normal distribution.
Okay.
Yeah.
Thank you so much. Let's